out while you guys are reading the problem. Let me get this. 3m minus 2, which is a natural, or 3m plus 2, excuse me. 3m plus 2 minus 3, which is the next multiple of 3 down, is equal to 3m minus 1. Okay. All right, now, both of these are legitimate to use. It's just the algebra turns out to be a lot easier if we work with the multiple of this multiple of 3. So that's why we wrote k this way. Now, just some comments about how that even happened. We're given an n, a natural number n, such that 3n plus 1 is a perfect square, and we want to show that n plus 1 is the sum of 3 perfect squares. It's kind of hard to get your mind around it, but we just start out with the direct translation here. By the problem statement, we have 3n plus 1 is equal to k squared for some natural number k. Now, the first implication here that's actually quite important is this implies that k is not a multiple of 3. And if k were a multiple of 3, then k squared would leave a remainder of 0 upon division by 3. Notice over here, k squared leaves a remainder of 1. So k is not a multiple of 3, and that explains this statement right here. Now, again, another subtlety here is it's very tempting just to do, well, 3m plus 1 and 3m plus 2. Those are the only two multiples of 3, that you would be working with in a problem like this. So why not use them? And you can. I actually worked it out where you work with those. But algebraically, it's easier to use the next multiple. So that's where we get the k squared is equal to 3m plus or minus 1 quantity squared. When you expand this out, you get this. Okay, now notice we have two different representations for k squared right now. K squared is equal to this by the problem statement, and now we have k squared is equal to this expression. And so that's why we can equate them right here. That happens a lot in math. You get two different formulations for the same term, set them equal, and just see where the chips fall. Okay, now let's see here. The ones go away. Right here, what we do, folks, is subtract 1 from both sides and divide by 3, and we get this statement right here. Okay, we get this statement right here. Again, I did leave out 1, subtract 1 from both sides and divide by 3, and we get that n is equal to this. Okay, now this is pretty nice because we're interested in showing that n plus 1 is the sum of 3 perfect squares. So when you add 1 to n, you actually get this statement right here. Okay, and again, that's pretty straightforward right there. You get that statement when you add 1 to both sides. But notice what happens here, something very, very nice. You can split up 3m squared into m squared, right? Plus m squared. Okay. Now we've used up 2 of the m squares from here, right? Now what's next? Okay, we'll have an m squared plus or minus 2m plus 1, but that's a perfect square binomial. So let me write that down. Plus, what do we have here? M plus or minus 1 squared. And that's a perfect square, and it's 2 different ones, in fact. Quantity squared, folks. That's quantity squared. Let me erase that. Okay. So this is going to be m plus 1 quantity squared right there, ladies and gentlemen. So you see this is 3 consecutive squares. Now it didn't say they had to be distinct. So 2 of the squares are the same, but the second one is m shifted 1 to the left or 1 to the right quantity squared. Now let's work a concrete example here. Work a concrete example where we write it in the form, let's see, we can write down 121 squared, right? 121 squared, or excuse me, what do we need here? Not 121 squared, 11 squared, right? So 11 squared is equal to 121. And this is just a concrete example to make sure this makes sense. That's equal to 121, but that's equal to 3 times 40 plus 1, which is the form that was originally mentioned in the problem statement. So we can write down 3.40 plus 1, right? So folks, as far as the original problem, our n is going to be this 40 right here, okay? The n is going to be equal to 40. Let me get that circled. That's what we're interested in. If we add 1 to that, the claim is we can write it as the sum of 3 squares. Okay, now let me get more space here on this cool Mac Air that I own now. Okay, so n plus 1 is equal to 41. Okay, and again, that's what we're doing. We're trying to show that this, that this n plus 1 that you see right here is the sum of 3 perfect squares. And so we have it written down right here. N plus 1 would be equal to 41, right? We took our n to be 40 here. So that's equal to 41. Okay, equal to 41. But notice what that's equal to. That's equal to 4 squared. Plus 4 squared. You see, not necessarily distinct squares. So 4 squared plus 4 squared is 16 plus 16, that's 32. 32 and 9 is equal to 41, but 9 is also a perfect square. So we get that 41 is equal to 4 squared plus 4 squared plus 3 squared. And that is that, folks. Now we proved it right here. This is the proof of the statement. Given those unusual initial conditions, we actually showed that an n with satisfying that initial condition, if you increment it by 1, it can be written as the sum of 3 squares. Now I did the one on the low side. If you play with some other numbers, you'll get a number on the high side. Notice that this would be the m-1 version of things right here. This would be the m squared. But in some cases, it works out to where it would be m plus 1 quantity squared. Anyway, I thought it was a pretty neat problem. You guys let me know what you thought about that.